All right, yesterday we finished. I can wait. Yesterday we finished with our first reaction on monosaccharides, the acylation reaction, and we said in the example of D-glucose on the left that you could acylate all of the nucleophilic positions, and this is a way of protecting all of those alcohol groups, right? All right, trivia question. Is this alpha or beta D-glucose?
Alpha. The one on the left or right?
The one on the left.
Alpha. Beta. It is beta D-glucose.
How do we identify alpha versus beta?
Equatorial and axial.
Yeah, so what we're going to do is we're going to look at the anomeric carbon right there, and we want to identify the hydroxyl group. If it's in the axial position, it's alpha. If it's equatorial, it's beta. So this would be an example of acylation of beta D-glucose going to the acylated product.
Can you give a quick definition of anomeric?
Yeah, so the anomeric carbon is the carbon that used to be the carbon on the aldehyde. That's the simplest way to think of that. And in this case, the stereochemistry from this can flip when it ring opens and ring closes again. So we talked about D-glucose. When you dissolve this in water, it will epimerize to the alpha D-glucose, so you'll lose the stereochemistry there if you put it into water. And that's called butyrotation.
So you always want to have that group with one carbon and the hydroxyl group? Is that always going to be there?
In D-glucose, you always have that coming off. Yeah. All right, so now let's go to our next reaction. Yep.
How are they going to draw on the ACS?
I'd have to take a look at the ACS workbook. I actually haven't looked at it for the carbohydrate section yet. All right, now let's do alkylation. All right, let's do the same example with alkylation. Sorry, this isn't the best looking glucose I've ever drawn, but it'll do. And this time what we're going to do is we're going to react it with methyl iodide in excess. And what do you think that methyl iodide will do? It's going to alkylate every single nucleophilic position, right? So in this one we've got 1, 2, 3, 4, 5 different alcohol groups that can act as nucleophiles. So that's exactly what happens. The good thing on the ACS is you do not have to draw chair structures because it's a multiple choice test.
But you probably need to be able to visualize them to answer several
Yeah, you may need to visualize them. We'll go over test taking strategies next week. Oops, sorry, I forgot my methyl groups. And there's also one other thing we need to do, because if you think about when these alcohols attack methyl iodide, there's still a proton on the alcohol, so we need to add in a weak base. And in this case, it's a very specific base for this reaction. It's silver oxide. That way we prevent epimerization. We want to keep the stereochemistry here. If we do sodium hydroxide, we can actually scramble some stereochemistry. So in this case, we use a weak base. All right, so pretty simple SN2 reaction. Just treat with weak base, and you can alkylate all of those nucleophilic centers. All right, now the kind of tricky derivative. And these are called glycosides. So in this example, what we're going to do is use D-glucose again. And we're going to treat this with an acid. So in this case, we have equilibrium conditions with our acid. So the most reactive alcohol on our sugar is always going to be coming off of the anomeric carbon. So we can protonate that. Now we've turned it into a good leaving group.
Dr. Engel?
Yep.
Why doesn't the oxygen with two pair of electrons attack?
Are you talking about the ether position?
Yeah.
In that case, it's not as good of a nucleophile as an alcohol. Alcohols are much more nucleophilic than ethers. The question is, well, why doesn't it do this with the other alcohols? It does, but this is the only one that's stabilized after it falls off, and I'll show you what I mean by that. So in this next step, we have this equilibrium where this one can get shoved off. None of the other alcohols can get shoved off after they become protonated. So in this case, this is highly stabilized. So now we've got a double bond there, oxygen with positive charge. And so this is resonance stabilized, right? So we could draw resonance structures of this. And then in the next step, we could have methanol in solution. So this can go and attack our methanol.
What is that?
What's that? The homie? Let me slide this over a little bit. And we still have a proton coming off of there. And then what do you think the last step is?
Wait, is the alkene attacking the methanol, or is it the other way around?
Well, you can think about it this way. The carbon that's... thank you. I goofed on that. I was going too fast. It's attacking this way. Sorry about that. So the nucleophile in this case is the oxygen, and it's attacking that carbon that has partial positive character. Good catch, Ian.
You're just jealous because you didn't hit it.
And then in this case, you lose a proton. So we'll do a deprotonation, typically with water, because these are normally in buffered solutions. So in this case, we end up with a new alkoxy group. Off the anomeric carbon. All right, so the kind of neat thing with this reaction is that this can also work with nitrogen nucleophiles. So in this case, I showed methanol attacking in. It can occur with longer alcohols or nitrogen nucleophiles. So let's make a note of that. And when you react these with nitrogen nucleophiles, they are called N-glycosides. So an example of an N-glycoside are our DNA base pairs, where if you actually look at them, it's a sugar attached to a pyridine base. So in this case, the sugar is doing the same sort of reaction with a pyrimidine base in order to form an N-glycoside. Your problem of the day looks at doing this mechanism with aniline, so you should be able to draw these out on the exam as well. All right, there's another reaction. And I'm going to switch to drawing these in the Fisher projection form, and you'll see why. This next reaction is called epimerization. What does it mean when things are epimers? Yeah, we talked about this yesterday. An epimer is when you've got a complex molecule that's only different at one stereocenter. So epimerization, you can do this with sugars and change only one stereocenter. So I'm going to draw glucose here in the Fischer projection form. And if we think about glucose in the open chain, it's technically an aldehyde. It's not favored in its open chain. It would prefer to be closed, but there's always going to be a little bit in solution that's open chain. And if we take glucose and we treat this with sodium hydroxide, we can actually get a strange looking product. Let me draw this out. It's essentially like an enol of our aldehyde. It's not favored in solution. It's very, very fleeting, and so it's actually impossible to isolate this. But what we call this is an enediol. Let me actually do this in blue. Simply because we've got an alkene with two alcohols coming off of them. It's very, very unstable, though. Because it's unstable, it really, really wants to go back to the aldehyde form. And so it will try to get away from that enediol. And when it does this, we'll get two different products out. We'll get this product.
No, let's have one more. Lengthening.
Did I miss one?
Because it's OH, H, OH, OH, and then the other one's just H, OH, OH.
So we should have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5,
Oh,
6.
I see.
Yeah, so one of those is now a part of there. So we haven't gained or lost carbons. And so you'll get this product, and you'll also get a new product out, or a different product, excuse me, where the alcohol on top is on the opposite side. And so if we look at this, what we've got is D-mannose and D-glucose, which is interesting because if you look over at what we started with D-glucose. So the problem is if you take D-glucose and you throw it in a basic solution, you'll actually scramble the stereocenter at this top carbon, and you'll lose stereochemistry, or lose the stereochemical control you had there and actually form two different sugars. So if you actually look at the early history of sugar chemistry, they had no idea what these sugars were, and when they would react them with sodium hydroxide, they'd form two new sugars, and they could tell that by melting point. And so this was how they actually elucidated all of the different structures of sugars that were on those family trees that I showed you. So remember that epimers differ in only one chirality center. So these pairs are epimers. All right, let's do another reaction that's very, very straightforward. When we
Biology for diastereomers?
So diastereomers are the parent class. This is one very specific type of diastereomers. So what you would call this are C2 epimers, because the stereochemistry got scrambled in the C2 position. Diastereomers could have more than one stereocenter flipped. Yeah. All right, so now let's look at reduction. And do we need the open chain or closed chain form for glucose in order to do reduction? What do you guys think? So we can reduce aldehydes. Can we reduce hemiacetals very easily? No. So we need to have it in the open chain form because we know how to easily reduce aldehydes. So now let's draw our open chain Fisher projection. And I'm just going to stick with D-glucose because it's the one I always remember how to draw.
That's the one we tested on.
All right, so we've got D-glucose. If we want to reduce this aldehyde, what do we need? What reagent do we need to reduce an aldehyde? Let's not fire a cannonball at it. Let's be gentle. NABH4. It's much, much easier to use NaH because you can put your sugar into water, get it to ring open. Sugars oftentimes aren't that soluble in organic solvents. So in this case, I've never seen it done with LAH.
I understand. No, like on paper, does it work? No. Shh, it does. Wow, yeah.
And so you can reduce that aldehyde to an alcohol. Nope. I goofed on this, sorry. Hydrogen, hydrogen, OH, and hydrogen. There we go. And what these are called are alditols. That simply just means that it's a reduced sugar. All right, I need to move this guy down. I will show you a video. The video I think is
I
coming.
hope it's not like 30 seconds long.
I've got some good videos. I've got 2 videos today. All right. So reduction is pretty straightforward. It's chemistry we've seen before. What do you think the next reaction is we're going to talk about? It's the partner to reduction, oxidation, right? Talk about this non-stop in chemistry, it feels like. Yep. All right, so for oxidation, got OH, H, OH. Hey guys, there's a lot of side conversations going on. So we've got D-glucose. Let's try to just oxidize our aldehyde. If we oxidize it, what will it turn into? Yeah, carboxylic acid. So we can actually change the oxidation state of a carboxylic acid. And when we do this, we can change this into a new functional group. And conversely, we can do chemistry on this carboxylic acid now. All right, so now we've got a useful functional group. And what these are called are aldonic acids. So we started out with an aldose, and now it's a carboxylic acid, so aldonic acid. We have to use very, very special conditions for this reaction. What we do is we react it with bromine and water, and it has to be at a pH of 6. And this is a unique reaction because in this case, it will only oxidize the aldehyde. We don't want to touch the other alcohol groups. We only want to oxidize the aldehyde. if we change the pH too low, it'll start oxidizing a bunch of other stuff in this molecule, which is actually what our next reaction is.
What's different?
The carboxylic acid, right?
Oh, the H.
Yeah, so we reduced or oxidized our carboxylic acid into or aldehyde into a carboxylic acid.
Can I use that for other synthesis problems?
It doesn't, you could. It has to be water soluble though. So normally with a long chain organic acid, oftentimes those aren't water soluble, so you got to be careful there. All right, so let me slide these down. I didn't judge these YouTube links very well.
What was the reagents? Br2H2O.
Yep, and pH of 6. Yeah. All right, now let's look at harsher reducing conditions. Where did I put it? All right, the next one is the harsher reducing conditions where we want to reduce more than that aldehyde. Nope. All right, so the next one, we're going to oxidize the aldehyde. And then what do you think the next spot is that would be most reactive towards oxidation? Yeah, the alcohol in the end, because it's a primary alcohol, can also get oxidized. The tertiary alcohols or whatnot are a lot less reactive towards oxidation. All right, so the reagent we need here is going to be a much, much stronger acid. So we can use nitric acid, water, and heat. And we'll actually go to, oops, sorry, that top one should be a carboxylic acid too. So now we've converted both of these to carboxylic acids. And this is referred to as an aldaric acid. And again, these can be synthetically useful as well. No, you do not need to know the mechanism for that.
Why are you drawing them like this?
With the Fisher projection? No, that's a fair question. Why am I not drawing the closed chain form?
I don't know, I wish
They're
they're
not
not.
as reactive.
Because in the closed chain form, we don't have an aldehyde, right? So in the open chain form, in equilibrium, we do have an aldehyde that is much, much more reactive than the hemiacetal in the closed chain form. So in this case, I'm always showing the open chain form for oxidations and reductions because we need to do those on the aldehyde. Yeah.
I think she likes spotlight better than this.
Yeah, this is a pain.
All right, so I've got a question for you guys. Why don't we use Na2Cr2O7 H2SO4? All right. So let me pull up the video here. And we'll see why we don't use this. I would love to do this in here, but they didn't install fume hoods in this room. So some chemistry lecture halls actually have fume hoods, and I've done this demonstration before because I like it.
So you should just do it in lab 6 and then the rest of the lab.
We're going full volume here.
So don't try this one.
Oh, shoot.
Yes, I know I'm more better than you're already glad.
All right, so he's pouring out regular plain old sugar, and in those oxidizing conditions, we use
Now
sulfuric
go ahead,
acid.
make sure that's all even, and then you can go ahead and carefully add the sulfuric acid. So you want to add just enough so it saturates all of the sugar. And at first, it's not going to be saturated, so that's why you need your glass stir rod. So go ahead and take note of the color of this reaction. It's going to start out as kind of tan, and then as you can see, as I'm stirring it, parts of it turn black and parts of it are getting more dark brown. And even though you can't feel it or smell it, it kind of smells like, well, burnt sugar. And there's a lot of heat coming off this right now. It's getting really warm. So I'm going to go ahead and stir this. And as you can see, basically now it's a really dark brown, almost black. And that's what we want.
This is the same reaction when you spill sulfuric acid on your clothes, burns holes through them.
So right now it's getting really hot. I can hardly keep my fingers on there anymore. And that's why I got these tongs right here. So I can go ahead and handle it. I'll try to move this a little bit closer. Now I'll just go ahead and make sure that, wow, this is moving right.
And this is why we have to use gentle oxidizing reagents when we're handling sugar. Yeah, it actually turns it all into carbon, so he's left with essentially charcoal when he's done.
So that, again, is sulfuric acid, 98% concentration, and pure table sugar.
So kind of a neat reaction there. But it's a good video demonstration of why we don't use sulfuric acid when we're reducing sugars. It's complete and utter overkill. Not easily. This wouldn't be something you want to do at home. It's very dangerous.
That's what I was just saying.
All right, so let's talk a little bit about what's going on here. And then I've got a second video for you guys that I like too. All right. So the sugar in these examples got oxidized. Chem 110 question. In this case, if they're getting oxidized, are they the oxidizing agent or the reducing agent? Yeah.
We're not that.
They're reducing agents. Therefore, they are called reducing sugars. The key for identifying a reducing sugar is to look at that anomeric carbon and identify the substituent coming off of it. And reducing sugars have an alcohol coming off of that anomeric carbon. And when they were first studying sugars, this was a pretty big deal. Was, all right, how can we identify whether or not it's an aldose or a ketose? And there's one really cool test you can do, and this is the second video I wanted to show you guys. It's called the Tollens test. So in this case, if it's the reducing agent, it's going to give up electrons, right? So it's giving electrons to something else, in this case, the oxidizing agent. So one test you can do is to take metal ions like silver or copper and give electrons to them, and you'll actually see what happens when you give electrons to them here.
What is going on, guys? It's Bucky, and welcome to the third episode of Don't Try This at Home.
So we're going to start off with a flask that contains a solution of silver nitrate.
So he's got silver
I'm
ions.
going to add a little bit of ammonia. And as the ammonia, you'll see that it's forming a sort of brown colour. We'll keep on adding the ammonia. In a minute, the brown colour
Yeah, the other red.
will disappear. But that's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide.
So he's basically
That's
trying to
now
make a
forming
solution
sort
of
very
nice
dark
silver
brown black
ions.
material. So now I'm going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. Let's take a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose.
So the
I'm gonna
glucose
put
is
this
going
on,
to give up its electrons.
Put a clip on. I'm going to give it to you, Dylan, and I want you to hold that. Really hard shake, that's good.
Oh my god. Somebody needs to call CPS.
So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid.
And there's fire in the
The actual material is silver. We're making pure silver metal.
This is awful.
Keep shaking. It takes about 3/4 of an hour. Is that okay? It does actually take a minute or two, but the harder you shake, the better it works. So keep shaking.
I like that he's having the kid do all the work. It's like, here, you shake this, I'll explain it.
It's being broken atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, you should see silver metal in the form of a mirror building up on the inside of the flask. And
He's almost
you've
done.
all seen those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, almost there. Keep going a little bit longer.
We'll be fine tomorrow.
Right, we're going to take the top off. Take out the stopper, just wash that off, and I'm going to pour out the remaining chemicals, and then I'm going to rinse this out with distilled water. Rinse it out a second time. Rinse out a third time. There we go. Now I'm just going to put that on, dry this off. And put the clip back on. And if you like to just give that little polish, we've got to hold it up by the neck. That's it. If we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go.
So this was actually how they used to make mirrors before modern mirrors were used. They used to actually use sugars as a reducing agent to collect colloidal silver on the surface of glass. Yeah, it's pretty cool stuff. That's
Christmas, yeah, what's gonna do that?
no, it just puts a thin film of silver on glass, and so this was commonly used for a very, very long time. And this was chemistry using sugars.
One of those experiments?
No, I actually tried earlier this year to do it with one of our tests, but we just didn't have all the reagents ready to go. Silver is actually pretty finicky.
We couldn't like order it or something for Christmas?
This is called the Tollens test. So if you do want to watch this video is super cool. It's an hour long, and he just does various chemistry experiments. So if you have kids especially, I'd really recommend trying to watch this video. I'll post it on the class website as well. It's very, very cool stuff I would love to do in this classroom if we had a fume hood and all the safety stuff. All right, so let's continue on to some new stuff. The new stuff has to do with changing sugars, so either shortening them or making them longer. So let's start with chain lengthening. And this is also referred to as the Kalani-Fisher synthesis. Yeah, same Fisher as the Fisher who described or came up with Fisher projections. He was one of the first chemists to study sugars. And the chain lengthening is a unique reaction. So let's look a little bit at this first step. That's Kalani Fisher. Yeah, sorry, my handwriting's not as good as it used to be.
True professor.
Like 5 years ago?
No, it's at the start of the year when I had more free time. All right, and we can react this with cyanide. And in this case, what will cyanide do with an aldehyde? It'll add in, right? So when we do this, what we end up getting is two different products, because that cyanide can attack from the top face or the bottom face of the aldehyde. And we end up with a pair of cyanohydrins. So we already saw this in our aldehyde and ketone chapter. But the next part of this, what we're going to do is we're going to reduce these. And what we're going to use is a poisoned catalyst. So we talked about Lindlar's catalyst being a poison catalyst. This is another poison catalyst that uses lead and barium sulfate along with hydrogen gas. And so just like Lindlar's catalyst, what do you think it'll do to that triple bond? It'll reduce it, but not all the way to the single bond, to the double bond. So just like with Lindlar's catalyst, it won't reduce it the full way. Instead, it will just reduce it part way.
Wait, why do you get 2 cyanohydrins from that?
Because that cyanide group can attack from either the top face or bottom face. So you end up with 2 isomers coming out of this.
Wait, is that palladium 4 or is it palladium with barium?
What's that?
The palladium and barium sulfate, are those two added together, or is it one or the other?
It's added together. It's just a big poison catalyst. Yep. And then the other product you get out is it's this guy. And you also have a hydrogen coming off the nitrogen, sorry. And we'll add in all of these. You actually can't isolate these, because what ends up happening is when you treat these with water, they'll immediately go to the corresponding aldehyde. And so if we look at these, what we have is essentially a new carbon. So we've taken our carbohydrate and we can actually add one more carbon onto the chain, but we don't have any stereochemical control, so we always end up with epimers at the C2 position. So these are a pair of epimers. You can't retain stereochemical control at all. All right, I think we have time to do the last mechanism. Very last one. Not for the year, but for...
I was gonna say, whoa.
Me too. I was like,
Last mechanism ever.
This is chain shortening.
you should throw confetti when we do the last.
And this is called the wool degradation. The wool degradation, I'll tell you, isn't synthetically that useful, but it was used during the early study of sugars to figure out how they were made, or sorry, their absolute configuration. So let's do the mechanism here. Yep. So again, we're going to start out with glucose. CH2OH. All right, so we've got glucose. Now we're going to add in an amine, specifically a primary amine. What will this do with the aldehyde?
Add it.
It'll add in. We'll get our enamine, right? So we've got a primary amine, which will react with our aldehyde to form our enamine. So we'll get a carbon-nitrogen double bond, and then the nitrogen will have an alcohol coming off of it. And these, if you remember back to those chapters, it's got a special name because it's got an alcohol group coming off of the imine. It's called an oxime. And then the next step, what we're going to do is take acetic anhydride, which in this case will convert this alcohol into a good leaving group. And then you also use a buffer system. So in this case, you do have some base around of acetic acid, so it's an acetic acid buffer system. And when you do this, you can convert this to your cyanohydrin. Fix this. We've got CN. Oops, I forgot one. Shoot. Let me move this up. Ah, shoot. I keep on mixing these up. Sorry, guys. That was a big yawn. All right. So we've got cyanohydrin.
The other two are backwards still too.
So the other ones are wrong?
Sorry. I'll just, how about this? I'll fix it for you guys. Let's do OH. This one's H. It's a different sugar than glucose. We should just be aware of that. There we go. All right, so now we've got our cyanohydrin.
Did you change any of the top one or not?
So I was just trying to keep the sugar the same. So we've got, if you're counting from the top down, on the right side we've got alcohol, alcohol, hydrogen, alcohol. I just wanted to keep it the same. Sorry. And now what we have too is we've got cyanide, which can actually act as a relatively decent leaving group. So I'm going to draw this bond out. And if we've got sodium methoxide around, what this will do is come grab this alcohol proton, clamp down, kick off our cyanide, and we actually lose a carbon in this step. And you end up forming an aldehyde along with a cyanide ion. So in this case, we lost a carbon. Yeah, in this case, when they were trying to elucidate the structure of sugars, what they would do is lop off carbons one after another and then try to match melting points to sugars they already knew. And so synthetically, the yields are very, very low, but it's useful for trying to lop off carbons and figure out identities of other sugars. All right, so I think we're going to hang there for aldehydes. Tomorrow when we come in, we're going to talk a little bit about disaccharides and polysaccharides, and then that will be the end for the carbohydrates chapter. I tried to cut down the sapling problems a little bit, so there's, I think, 23 now, not 40. But I would still try to go through and complete as many of those as possible. It'll help you study for the exam.
So what are we going to do after that?
We'll do peptides next. Just one second.